Okay, we are starting lecture number 10. So last time we have defined conditional probability, which is probability of A given B, and this is a definition. So this is probability of A intersection B divided by probability of B. Okay. So as I have said before, A shows a set, B shows another set. So what I know is that event B, a set, this has occurred. Okay. So given that, what is the probability of A? So as you can imagine, this is something like this. In the sample space, I have, let's say, all of these outcomes associated with event B. So I know that this has occurred. Now, what is the probability that A has also occurred? Okay, so let's say that this is the outcomes forming, let's say, event A. So you can imagine that as soon as I know that B has occurred, so in the sample space, so my sample space effectively reduces to this part, reduces to B, because I know that B has occurred. The other parts have no probability. So you may say that this is the ratio of this part. Well, let me mark with this red part overlapping inside of the B, A intersection B, and the ratio of this and that. So how do I calculate the ratio of two sets? I need to find a measure of their bigness and smallness. This is the probability measure. So we are assigning a probability to this intersection set and comparing it with the other set. So of course this will be taking the value of 1, let's say, if this red set gets larger and larger and larger. So in other words, if A is equal to B, then I have B intersection B divided by B in that case, so I have 1. Okay. So this is the definition of conditional probability, and as soon as I have that, I have Bayes' theorem, which is probability of A given B is equal to probability of B given A times probability of A divided by probability of B. Okay. So this is immediately resulting from this definition. The reason, let's move this term probability of B to this side. Then I have A given B times B. So A given B times B is A intersection B probability. Okay, so I have on the left side A intersection B probability. If you check this one, this is the same. In other words, I move this to this side, and I again, if I interchange A and B, I get the same rule. I get the A intersection B probability. So this is the Bayes theorem. So these are the most fundamental results, okay, that will be used in applications and so on. Okay, so today let's start with, let's say, two random variables. We have two random variables. Let's say I have X and Y. So if I have two random variables, what can I do? Well, an important fact is marginalization. Okay, so this is the following. Fx of x is equal to joint density of x and y. So let me put x naught for specific number, let's say. Okay. So this is called the marginalization. So this is the joint density of x and y, PDF, joint PDF of x and y. So I marginalize over one of these variables. Marginalize means integrate out. Okay. And I get this. So if you interpret this as a probability, well, how do you interpret it? Let's assume that I multiply this part by epsilon, this part by epsilon, then it becomes almost like a probability. Okay. So let's assume that it's multiplied by some constants. So right now it carries the measure of probability. Okay. by epsilon multiplication, then you can see that for every x naught, I am adding, x naught is fixed over here, I am adding up, if there's an epsilon over here, all possible y's, okay? So that's the meaning of that. For you fix this x naught, in this joint density, you list all of those y probabilities for which this pair occurs, then you sum their probabilities up, okay? Well, this is a marginalization, so how can I show this? If I need to show this, well, I will do the following. Of course, we approach from CDF point of view. So what can we do? So we can define maybe a probability of, well, let me define some sets in this case. So what do you think about this? Probability of random variable x smaller than, let's say, x naught, and random variable y smaller than infinity. Okay? Something like that. So there is a comma over here. As we have said before, this comma means the following actually. I have the intersection of two, let's say, constraints, sets, and so on. Okay? Over here I have intervals. But clearly this second one is always satisfied. Y is less than infinity. So effectively, this is equal to x less than x dot. Okay? Well, I can also write this one in another form. Well, I can say that this is nothing but the area, because it's a probability. It's not the area, sorry, it's the volume under this or let me move this y, let me interchange. Okay, I have something like that. Okay, so I'm trying to cover this area in the integration limit. So what do I mean by that? So I have x, I have y over here. So x is less than x naught, and y is, I can take any value, as you see. So I'm trying to cover this area over here. So x ranges from minus infinity to x naught, to this part, and y ranges from minus infinity to here. So if I integrate this density function over this area, so I calculate this volume over this area, okay? Density function gives the height of this, volume. So height of this function. So if I calculate the volume over here, so I get this probability, okay? That is it. But I know that this probability is nothing but, by the definition of CDF, it is this. So from this part on, let me move over here, then fx x naught is equal to minus infinity x naught x prime y prime dy prime dx prime. Okay. Well, I can take the derivative with respect to x naught, or I can call this x if you wish. But if I take the derivative with respect to x naught, I get the density function. So how do I take the derivative of this? So this is something that we evaluate. Okay. After this inner integral evaluation, y prime disappears. So this is the function of x prime only. Okay, whatever this function is. Then I'm integrating over that x prime also, I get a numerical value of this function. Okay. So if I take the derivative of this, then if I call this, for example, a gx prime function, this part. So what do I get? If I take the derivative of this, well, I get, let me call this small g, okay? If you integrate, well, if you take the derivative, you get this minus g of minus infinity, and that is it, actually. If you want, let me explain this a little further. So I have g of x prime dx prime. So this is differentiated dx naught. So this is minus infinity. So this is dx naught g x naught minus g minus infinity. So if you take the derivative of this, you get gx naught. And this is just a constant. If you differentiate it, it's equal to 0. So I get gx naught. So this is called, differentiation under an integral sign. Okay? So how do you do this? If you are differentiating this integral, so with respect to this x naught, well, there are some possibilities. X naught can appear at the limits, x naught can appear in the integrand, and so on. So this is called differentiation under an integral sign, and this is the way you operate actually. So at the end, I get jx naught. So this is minus infinity to infinity fxy x naught y prime dy prime. Okay. So gx naught is, as you see, I need to put x naught instead of x prime. So what was this? This is equal to this. And this is, marginalization property. Okay? That is it. Okay. So this is the way you do calculation with densities. Okay? So if you have probabilities involved, it is easier. Probability mass functions, let's say, it's easier. But if you have densities, well, in general, this is the way you do the operations. It's a little bit, you have to be somewhat more careful in the calculus of these results, but that is it. Okay, so we have, I'm erasing this proof part. Let me erase this part also. Okay. So what else? Now after that, we have something called total probability theorem. And this is the last one about probabilities. So let me have something like this. Probability of, let's say x. Well, let me say x is equal to k. Give x is equal to k. Okay. So this is equal to okay. This can, let me have, okay, since it's a probability, I'm talking about probability mass functions right now. Okay. So this probability mass function, I'm calculating this probability. So how can I calculate this? Well, what do you see over here is this product, again, follows from this one. Let me see. Follows from, well, joint density is this one actually. A given B times B is their intersection, okay? Joint density. So I have probability of x is equal to k, comma, y is equal to y. This means their intersection, as we have said, this product. So again, this is nothing but the marginalization, as you see. So I'm fixing one of these variables and summing up, this time exactly probabilities, because this is probability mass functions. Why do I say so? As you see, y is an integer ranging from here. So k is an integer over here. I should define them properly, but as you can imagine. So I'm summing up all of the probabilities for y for which x is equal to k. Okay? That is it. Well, what is interesting is that this is the conditional probability and this is the marginal probability for y. In many calculations, marginal probability or this conditional probability or both of them can be easy to express, and you can get this result, the left hand side, very easily in some of this. And this is called total probability theorem. You can say that this is not different from marginalization. Of course, you are right. Okay? If you have continuous random variables, then you have this. As you can imagine, their product will be joint density. Joint density, and one of these variables are integrated out. Okay. That is it. For the continuous random variables, we have that. So let's have an example illustrating this. So let me see. So this example illustrates the usage of this total probability theorem. Now I have a sample space. From this sample space, I'm generating a random variable x. Okay. Now I will describe the generation process. We throw an unbiased coin. Okay. If heads show up, then x is equal to 1, else x is uniformly distributed in 0 to 2, let's say. Okay, something like that. So what's the question? Find the density of, let's say, random variable x. Okay. Let me have this capital variable. X's random variable is uniformly distributed in 0 to 2, and so on. Okay. Okay. So how can I handle this? Now I will do the following. Well, solution. I will try to calculate probability of, now, x less than or equal to, let's say, x. Random variable is, so this is the CDF. So how can I calculate this? Well, how about this? Let's use this total probability theorem. So this is probability of x less than or equal to x, given that, well, let me call this theta is equal to heads. Theta is the coin throw is equal to heads times probability of head plus probability of x is equal to x, theta is equal to tails, the other event, and probability of tails. Okay. So can I do this? Indeed I can do this, because this is nothing but this probability calculation. Probability, I could have written, any event. I could have written A over here. Okay. So, as you see, for this event, I am marginalizing over this coin probabilities, coin event. Okay. So how can I do this calculation? Well, I will try to, let me write this one more time, because I cannot see that part very well. Okay. Now, how about this? If I know that this head event has occurred, so what does it say? If heads show up, x is equal to 1. So this is deterministic. Okay. So this x is equal to 1. If this has occurred, as you see, it's easy to identify this, because I know this case. For this case, small x is equal to 1. And there are no other possibilities. So how about this probability mapping then? Well, let me sketch this function. So 1 is the critical part. This is this probability of x given theta is heads. Okay. So as you see, well, if I set this x, so it's a function of x, as 3 over here, so I know that at this event the random variable takes the value of 1. Okay, by the definition, random variable is equal to 1. So it will be reaching probability of 1 at this level. So as you can see, so it is taking the value of 1, and this is empty. It is 0 elsewhere. Okay. So if it is heads, then random variable takes the value of 1, and if you are looking for the interval including, let's say, this 1 minus infinity up to 3, the probability is 1. If you have minus infinity up to 0 interval, then the probability is equal to 0. Okay, so this is this function. Now probability of this is unbiased coin, so I have 1/2 over here times 1/2. This function times 1/2 plus. So how about the other one? Well, the other case, now it says that it's uniformly distributed. So probability, so I'm sketching a function as you see. Actually, this is the CDF function given theta is equal to this. Okay, this is the CDF function. So this is a function of x. So I'm trying to sketch this function. So this is a uniform distribution. So what is a uniform distribution? Well, uniform distribution is this. Sorry. In 0 to 2, then I have this. Well, the area should be equal to 1. So then the rectangle has the, let's say, peak value at 1/2, and it goes up to 2. All other density values are equal to 0. Okay, so that is the PDF, but I need the CDF as you see. So CDF is, well, it's a linear function if you integrate that. It's a constant function. This integral is a linear function, and at which point, so it ends up over here, and it will be taking up the value of 1, at this point 2, and that is it. So this is this function. Of course, I can write these functions algebraically, but it's easier for us to do this. Now I should do this addition. Then the resulting function is the final result. Well, this goes with the slope of 1/2 up to 1. I think it will be clear at this point. And at 1 there is a jump of, not 1/2 actually, at 1/4, because 1/4. Slope is 1/2, but there is a 1/2 factor over here. Okay, 1/4. Now this is a jump of 1 unit times 1/2, 1/2 unit. So it jumps to this level, 3/4, and this is open, and it goes with the same slope up to 2. Am I right? Up to 2, then it is equal to this. So this is CDF of x. Okay. Slope is again 1/4. So these two lines are parallel. Okay. Because this is just this function plus this function times 1/2. Okay, that is it. But the question was CDF. So how do you handle CDF? So this is, sorry, the question is PDF. So we got the CDF. So I need to take the derivative of this. Okay. So I take the derivative of this to get. So what do I get? Wow. So easy part. After 2, derivative is equal to 0 because it's constant function. There is no, 0 slope. Over here, this function again, it's not changing at all, it's 0. So I'll write the result. So in between 0 and 2, it is, well, slope is 1 over 4, and at 1, there's an impulse. Okay, and this impulse has, let's say, weight 1/2. Okay, so this is our CDF function. In some early courses, instructors avoid using impulses in probability course. Okay, because maybe rightfully they think that manipulation of impulses will create a difficulty and so on. But at the graduate courses, you are welcome to use impulses. Okay, so if I use these impulses, what's the advantage of using an impulse? As you see, I introduce, because of this discontinuity, this is a step kind of discontinuity, so I can write this function, remember from circuit theory, this is a ramp function. Ramp function is actually going on like this, plus a unit step function, and there are 1/2s. Okay, that is it. If you take the derivative of this, ramp function has derivative unit step, and step function has derivative impulse. Okay, so this is the magic of singularity functions. Unit step function, impulse function, and ramp function, and so on. So I'm allowed to differentiate if I introduce impulse functions in my calculus. Okay. As I have said before, in undergraduate courses, instructors try to avoid this. Maybe they think that if I introduce Dirac delta function, this will confuse students in terms of when they do calculations with probability mass functions and so on. But I mean, if you know what you are doing, there is no confusion, and it's much more easier to handle. Right now, I can show both continuous and discrete random variables together with impulses. So what is the area under this? Well, the area is, well, if I integrate from -infinity to infinity, it's the area of this, 2 times 1 over 4, 1/2. Then the area of this, if I cross over this impulse, is 1/2 also. 1/2 plus 1/2, I get 1. So it seems everything is in order. Okay. So let me write a note. Of course, I can solve this problem much faster, but this is just an illustration. Now, I'm allowed to right now do things like this. Fx of x, marginalization or total probability theorem. Now I'm -infinity to infinity. Fx theta, as you see. So let me mark this theta with small theta, but I don't know how to make it. So let me mark it like this. So this is a random variable. This is small. Okay. D theta. So this is our, marginalization rule or total probability theorem. Just we have seen a few seconds ago. Now, as you see, the advantage of random variable is this. Now, I have to say over here heads and tails. Well, it's a difficulty. But instead of that, if I consider, for example, heads is equal to, let me write with some other color. Heads is equal to 0. Tails is equal to, where is the tail? Well, tail is not even introduced. Tail is equal to 1. Okay, 0 and 1. So this becomes a random variable essentially. So now you say that what is the variable of density of coin flop? It may result in 0 or 1. Okay, so you write it like this: 1/2, or let me write probability of heads times theta impulse, probability of tails times theta is equal to 1. Okay, so this becomes this density. So as you see, I'm again using impulses. So this density is probability of heads 1/2 and 1 probability of tails again 1/2, and there are only 2 outcomes. Okay, this is the density f theta theta. Okay, now if I integrate this, now you see the following. This is equal to, just do the integration, then probability of heads, because of this impulse, this integral is evaluated using the impulse calculation rules. Now this is the variable of integration, as you see. X given theta is equal to 0 plus probability of tails x given theta is equal to 1. If you introduce impulses at the very beginning, now I'm calculating an integral involving an impulse function. So whatever this function is, this function, once I multiply by an impulse, it will be evaluated by theta is equal to 0. So I substitute, whenever I see a theta over here, I substitute a 0. Plus the second one, whenever I see a theta over here, I substitute a 1. Okay. So if you do this, as you see, it's a little bit faster. Now, how about this density? It says that heads show up, then x is equal to 1. So this is a deterministic density. So this is x is equal to 1. Because there are no other cases. If I introduce impulses again, so this has a probability of 1, as you see, times this impulse. How about this one? This is uniform distribution of x, let's say in 0 and 2. Well, this is, I think, in 0, 2. So, an impulse at 1 times 1/2, because probability of heads is 1/2. Uniform density times, again 1/2 probability of tails. This is the final result. Okay. So this is called mixture for maybe more experienced students. This is called mixture of two distributions. Mixture of two distributions. Okay. Distribution number 1 is uniform. Second distribution is, it's deterministic, but I can put any distribution over there, as you can imagine. Okay. And this is called theta is, in many cases, this is called latent variable. So you don't observe this. This is a hidden variable of this problem. It's a problem, let's say. Latent variable. So we are integrating out overall possibilities for the latent variable. Okay. That is it for this calculation. Okay. So this is all about PDFs. So what we have learned actually conditional probability, total probability theorem, biases theorem, density calculations, and so on. Now, up to now, we haven't discussed this expectation operator. Expectation operation. This is, again, very important for our purposes, as you can imagine. Now, this is our notation, expected value of x. This is capital X. So, what's the meaning of this? Its meaning is, let me explain, it's as follows. Okay. So first of all, every expectation result becomes a scalar quantity. It's not a random quantity anymore, okay? Because, as you see, if I had instead of x a 1, this will be the area under this density function. But it's x times x. So what's the meaning of this? Well, it's actually have such a meaning. Let me explain. Previously, I have discussed this a little bit. Let's say that this density can take only two values. Let's say that it can take the value of 1. Let's say head-tail example again. X is equal to 0. Tail this. Okay. Let's say that I have such a density. Then how do you calculate this? Now you say that probability of heads times, let me change it a little bit so it will be more visible, 1 and 2. It takes the values of 1 and 2 times 1 plus probability of tails times 2. Okay. So what's going on? Well, it is this. Now in the sample space, I'm mapping all of these quantities to either 1 or 2 right now. This is the sample space as before. Okay, this is our random variable mapping. So all of these points are mapped either 1 or 2. Okay. So how can I interpret this? Now, if I do this random experiment in an independent manner many times, what happens? So let me do this. Okay. Okay. So let's say that I do this mapping independently. Let's say 100 times. Okay, number of trials is 100 over here. xk is the result of this experiment at the kth trial. Okay. So what is this? Average of all trials. Am I right? Average of all trials. So this is the outcome of the kth experiment. So I'm taking the average of, let's say, 100 trials. So can I write this one as follows? Well, okay, let me 1 over number of trials. Since this takes either the value of 1 or 2, isn't it? So this is 1 times number of times xk is equal to 1 plus 2. Since in this summation, as you can imagine, I either have 1 or 2. So I have maybe 51s and 52s. So this will be 1 times 50, number of times xk is equal to 2. Okay, number of times xk is equal to, that is it. Now if I move this 1 over trials over here, and over here then, so what do I get? So at the end, as you can imagine, we get this probability. Okay, how do I get this probability? As limit, so let me write over here, as number of trials goes to infinity, so I'm assuming independent trials. Of course, this is very practical. You repeat this experiment many times. So maybe you are asking a person's opinion on the street. So independently, you have different person and you are asking every person's opinion. So they're independent. You meet different people. You are not asking, you know, many, let's say, you are not asking opinion of family members and so on. Okay, maybe their opinion is somewhat like dependent to each other and so on. So as the number of trials goes to infinity, so what do I see? This calculation, so this is the empirical average. Empirical means experimental. So empirical average approaches as number of trials goes to infinity, expectation of x. Okay, so over here x is this random variable, it goes to expectation of x. So this is the reason that, you know, this expectation is important for us, because if I repeat this experiment many times, immediately I see that because of the definition of frequency interpretation of this probability, then this ratio will be probability of heads, number of times, 50 times, let's say, or sometime maybe out of 1 million experiment, let's say 500,000 and 100 times I have heads, and their ratio is almost like 0.5, okay, something like that. So this is the other case. So expectation operation enables us to study in a way the limit behavior of this empirical results, which are very important in practice. Now I'll write something maybe you will immediately accept after this discussion. This is a little surprising. We have to think about it a little further, but how about this? Now this is a function of a random variable. Okay. Now if I have a function of a random variable, what happens? I just put a g function over here, So I pull a random, from the sample space, I get these two random variables and I map them through a function. Okay? So as you can see, the generation process, you select an x. These x's are passing through this g function, and you calculate from this empirical average result. You immediately get that result because there is g of x of k over here. So number of g of x of k is equal to, let's say again, something. So there is a similar thing going on. So that is it. From this expectation result, they are interlinked. Okay. So I won't be proving this. Okay. So what else? Yes, we have, once we have that, given this, now we have some interesting results, moments. So expected value of x of k, capital X of k. This is called kth moment. Of random variable x. Okay. There is something called central moment. So what's that one? X minus expected value of x to the power k. Sometimes we denote this expected value of x as, this is m1. Sometimes we denote it by Xbar. Okay. So there is a notation for this, but I don't want to confuse you. This is called the kth central moment. Why it's called a central moment? Well, in this calculation, only difference is there is a subtraction going on. You are subtracting the mean of this random variable. So inside of this bracket, I have a random variable with zero mean value. But maybe I should first define the mean. So m1 is equal to x bar, another notation. Expected value of x is called, important for our purposes, mean. So it's in a way average, mean of random variable x. So similarly, sigma square is, this is second central moment, expected value of x minus x bar parentheses square is called the variance of, let me write at least this a little better, variance of random variable x. Okay. So mean and variance, they're important quantities, you will see, because we will be using in many cases Gaussian distribution, and Gaussian distribution has two parameters. In univariate or one-dimensional Gaussian case, mean and variance. Okay. So this is sigma square, our notation, and let me write sigma is called standard deviation. Maybe from some statistics discussions, 3 standard deviation, 2 standard deviation, and so on. This comes up in quality and some reliability measures and so on. We have standard deviation is the square root of variance. Okay. What else? Oh, okay. So why are we placing importance on these moments? It will be clear immediately. Well, so I would like to first discuss this moment generating function. So this is denoted as phi of s, and this is expected value of e to the s x. Again, all of these are reminders, okay, because I'm not teaching you anything new, or I'm not discussing anything new. This very fast review of probability, important facts. So what's the meaning of this? So as we have said before, now this is g of x. I have e to the sx fx. I have something like this. So again, as an electrical engineer, you immediately recognize this integral. So this is almost like Laplace transform. Well, this is now small x. Okay, because I'm taking numerical values for it, as you see. I'm integrating for it. So this is the Laplace transform of the density, but the only difference is, in the Laplace transform definition, there is a minus sign over here. So there is no minus over here. Actually, that minus is not needed. It will be simplifying our life. But let me write this. This is like Laplace transform of, but in the variable minus s. Okay, so this is Laplace transform. It's not needed, but just, you know, let's do not forget this Laplace transform in the variable minus s. Okay, so instead of s, I'm using minus s after the calculation of this transform. Now, why do we call this moment generating function? Now let me take, these are interesting facts actually, nth derivative of this phi function. Okay, so how do I take the nth derivative of this phi function? We move this differentiation inside of this integral. We don't discuss how and why. Okay, then I have this e to the sx function is differentiated many times, n times. I have s of n, e to the sx. I have this. Okay. Oh, sorry. I have x to the power n. Okay. Because I'm differentiating with respect to s. So x comes into the front. Now then I evaluate this at s is equal to 0. Then I get this expected value of x, x to the power n. Then I get nth moment. Okay. Okay, nth moment over here. So this is nth moment. So this is the reason that is called moment generating function. So if you can calculate this function, then in order to get these moments, only thing that you need to do is calculate this derivative and evaluate that derivative at that s is equal to 0. Okay. So what is the importance of this? Well, then we can do the following then. By Taylor series, again, I'm assuming some nice, let's say, density functions. By Taylor series of phi of s at s is equal to 0, we can write, so phi of s, okay. So what's Taylor series? This is an infinite series. This is n, right? N is equal to 0. So this is nth derivative at 0 times s over n factorial. Do you remember this Taylor series? So Taylor series is, you are assuming that you have an infinitely differentiable function over here. So this is Taylor series expansion at 0. Taylor series expansion at another point is, maybe s naught is, it becomes this s naught. So you evaluate the derivatives at s naught and multiply by this polynomial term, and you have an n factorial over here. But our cases, as you see, Taylor series expansion at, let's say, s is equal to 0. Okay. Okay, so if I do this, what do I recognize? Well, if this thing exists, then this is nth moment. So what do I see? Taylor series is nothing but a series whose coefficients are the moments, as you see. Of course, there is an n factorial over there, but moments is the critical part for our purposes. So knowing, let's say the knowledge of all moments Mn, let's say from 1 to, it goes like this, all moments, is equivalent to knowledge of moment generating function. Okay, because I can evaluate the series. Okay, assuming that I have convergence issues and nothing like that. In general, probability density functions are very nice functions because their area is equal to 1. Okay, meaning they're always positive. So I mean, there is not much that they can do, but there can be again problematic cases. Okay, but they are very nice functions in general. So you are allowed to do such calculations without so much, let's say, consideration, at least in engineering mathematics. So what I see is that if I know these moments, I can write this function. If I know this function, where is it? This function. Then this is the Laplace transform of the density, meaning that I can apply the inverse Laplace transform, then I get the density. Which is, so let me write this one more time, which is equivalent to the knowledge of the density. But the trick over here is you have to know infinitely many moments, okay? Otherwise I cannot, calculate that infinite summation. So that is the case. If we know moments partially, say first, let's say 2 moments, then such a characterization, such a, let's say, moment knowledge, such knowledge is called moment characterization or partial characterization, because I cannot fully characterize it. Partial characterization of, let's say, density PDF. Unfortunately, if I know only 2 of it, well, it's nothing, it's not very significant, but it carries some information, okay? It's not very significant, only the first 2 moments are present. But still it carries some importance. We call this a partial characterization of this PDF. Okay, so a few other things, and that will be the end of this lecture. But I have to mention these 2 also. So, conditional expectation. So what's conditional expectation? Now I have expected value of. Actually, this is also quite important. This. Now, as I have said, well, expectation evaluates this random variable. It maps this random variable to a real number. At the end, I get a scalar quantity. So this is an integration of over x, but now the sample space of x has changed. Do you remember our discussion of conditioning? Now after this, sample space, some parts of the sample space is maybe discarded. Okay, so I'm making note of it by this notation. Random variable of x after this conditioning. Okay, so once you have this density, now you can forget about the rest. This is x. So this is the usual dx. Again, I'm not discussing the discrete continuous cases, because if you introduce impulses, you have both cases together. So what's going on? Well, this is the density of x. think about it, forget about the details. This is the density of x after conditioning. And this is the expectation with this density. Okay, that is it. Now, of course, I can do things like this, maybe more interesting things. Again, a conditioning is present, but now I have function of x and y. Okay. So this is a function of x and y. So what should I do? Over here, I put a function of x and y. So this is equal to I should be a little careful because let me put y naught just to show it. Y is equal to y naught. This is small x. Okay, let me write capital X is equal to x. And capital Y is equal to y naught dx. Okay, so what's going on? So for the sake of this calculation, as you see, now y is fixed to y naught. I have that knowledge. So this is very nice because if it is something like y smaller than y naught, it will be very difficult. But if y is equal to y naught, now this random variable y is automatically fixed to y naught. So why that is the case? Well, we can discuss it a little further, but you may think about the joint density. In the joint density, any other value by taking y naught has probability 0 after this conditioning. Okay, so this is y naught. So I have this fixed to y naught after this conditioning. So on the random quantity is x. X is then average width conditional density of x, which is this. Okay, that is it. So as you see, now this is a function of, let me write function of y naught. Because if I change this conditioning, let's say if I change this conditioning value from 1 to 2, then of course this integral changes. The reason is this value changes and this conditional probability, conditional PDF changes. So it depends on y naught, obviously. Okay. This is a little bit confusing looking, but if you pay attention to the details, it's not so much confusing. So let me write the final result, iterated expectation. So this is over y. I have. Now, if you haven't seen this before, it would be very confusing looking, but this is just a reminder. Now, previously, we have calculated this part, isn't it? This is this result, conditional expectation. Now, I have random variable x, random variable y, but y is fixed to y, small y. Now, this is, let me call this a function phi of y, because it depends on this conditioning variable. Then I take the expectation over this y random variable one more time. Okay. So what is this? Well, it is equal to, this is the reason expectations are, very easy to utilize. It is equal to expected value of over the joint density of gx and y. Okay. So how can I show this very briefly? Well, let me go over here. So this is what? Minus infinity to infinity. This function fy of y dy. Definition of expectation. How about this function? Okay, let me write that function. That function is this g x y fx given y x given y, and I'm calculating this integral over this x dy. This is minus infinity to infinity. So this is conditional expectation, conditional density over the random variable x when y is fixed to, capital Y is fixed to small y. Okay, that is it. So this is this. Now, so this is this part, this bracket. So I write density over here. This is this density. Okay, and dy. Okay. Now this part is from the definition of, again, conditioning or conditional probability definition. This is the joint density of x and y. So I have gx and y times joint density of x and y integrated over dx dy. So this is the definition of expectation. Okay. So that is the end of this proof. As you see, this iterated expectation is also a very useful result, because by using this E notation, by you have seen that the conditioning is simplifying our life significantly in some calculations. So you divide the problem into many little problems by conditioning. Okay, so you fix one of the random variables, then you evaluate something and you do many evaluations like that and then combine. Okay, so you can do similar things as you see with expectation, PDF calculations, and so on. So the critical aspect is, as I have said, definition of conditioning, biases theorem, etc. Okay, that's all for now. So we will continue after some time.